Welcome everybody to the Scaling Ethereum workshop for Connext. I'm Eddie, an integration engineer at Connext, and I'll be walking through how you can use Connext to build a cross-chain application. So we're going to start with the docs site here at docs.connext.network. And at the bottom of the homepage, you'll find a bunch of helpful links, including a link to our bridge UI and the Explorer site. But right now, we're just going to jump into the concepts to do a quick review of what Connext is. So Connext is a modular protocol for securely passing funds and data between chains. What this means is that you can not only send assets between chains, but you can also send any kind of arbitrary data, such as data that specifies a call to a function on another chain. And what we're going to be doing in a few minutes here is walking through how to build a cross-chain app, or ZAP as we call them. One thing I want to touch on in relation to modularity is that we've built Connext as a system which derives its security from Ethereum, and it plugs into these canonical messaging bridges of each chain. So Connext is actually able to shortcut the normal waiting time for messages to be passed between chains by aggregating all the Merkle roots generated on each chain, passing them to Ethereum, and then verifying their correctness off-chain. This kind of faster optimistic layer expedites data passing as long as no fraudulent transactions are detected by monitoring agents or watchers. Otherwise, the system will fall back to the full waiting time for the chain's canonical bridge. And this mechanism gives you the best trust guarantees because we ultimately defer to the security of the underlying bridge used by the chain itself. And we just have this fast optimistic layer on top that's secured by a 1 of n liveness requirement, meaning only one honest watcher needs to be online at any time to fully secure the network. And that's not really a difficult requirement. In fact, anybody can run a watcher. So if you're really skeptical, then you have a trustless way to guarantee the liveness requirement of the network. Now, if you want to get a deeper understanding of the architecture and bridges in general, I invite you to take a look at this page, look through the rest of the pages and docs here. But for this workshop, we will focus solely on how to actually build something in Connext. So we're going to jump into the developer section here. And as a general outline of what we'll touch on today, we're going to look through a few examples of cross-chain applications using Connext, and then we will talk about a couple of critical concepts that are important to understand as a ZAP builder. So the quick start guide will actually walk you through step by step how to build a cross-chain greeter. It basically assumes that you have nothing set up. So it'll show you how to install all the prereqs and how to use Hardhat, which is a smart contract development toolkit, to deploy the contracts that you can just copy and paste from this page. But for this workshop, we'll take a slightly different approach by cloning this ZAP starter kit that we've built. This is just a GitHub repository that contains all the examples and docs, and it will be slightly more favorable for people who just want to have a running start with something that works out of the box. So let's open this up and take a look at what we're working with here. To build a ZAP, you are going to be calling a single function exposed by Connext on any of our supported chains. And that function is called xcall. And we will see very soon what kind of parameters actually go into this pretty shortly. But in general, you are going to be sending either assets or data to be used for a cross-chain function call, or maybe a combination of the two. But if you're sending data, there is a distinction to be made between unauthenticated and authenticated calls, which we will talk about later. And the call flow between the two chains that you're interacting with is going to look something like this, where you have some origin chain and some destination chain. You're going to be writing a source contract that's deployed to the origin chain, and that contract will call xcall, sending in the appropriate parameters, and then Connext's system will basically route that data and any sort of like asset transfer to the destination chain. If you happen to write a target contract and deploy that to the destination chain, you can specify that target contract as the target address that Connext will call, and Connext will basically be able to unpack any call data that you send in with the xcall and use that to call a specific function on your target contract. In some cases, you don't actually need to deploy a target contract. So if you're just doing something like sending assets across chains, you really only need to build one contract on the origin side. And we have an example of that called the simple bridge, which is just transferring tokens from a user on the origin side to some specified address on the destination side. And since there's no actual function call that's needed to be called on destination, you don't have to deploy a target contract. But for today, we are going to jump into a greeter example, and this greeter is going to do both an asset transfer and an unauthenticated function call. So what I mean by unauthenticated call here is that the target contract has a function that we want to call, but it's not permissioned in any sense. So it's not looking for some kind of owner. It's basically just completely open for anybody to call. So the context for this example is we have a destination greeter contract on the destination chain. It stores a greeting variable that we want to update, and the update greeting function is going to provide the logic to update that variable. And then we'll have a source greeter contract on the origin chain that uses xcall to send encoded call data, and then have that routed by Connext and called by Connext's system to ultimately update that greeting variable. Okay, so if you have cloned this repository, you can go ahead and basically take a look at what's going on in this example. So I've done the cloning. I've done the sort of setup that's laid out in the preparation steps here, which is including downloading Foundry, which is another smart contract development toolkit, downloading Make, and also minting myself some testnet tokens. So the easiest way to do that is actually just to go to our testnet bridge UI, and at the bottom here there's a faucet. So you can select whatever chain you want and then mint yourself 1,000 test tokens on any of those chains. But we're going to look at the greeter example here. So that's in source, contract examples, and greeter. You'll see two contracts here that are basically fully implemented and ready for you to deploy. So we're just going to talk about what's kind of happening in these contracts. So starting from the source side, this is the one that will be deployed on the origin chain. The first thing we do is we need to import these interfaces. So the iConnext interface is the interface that will contain the xcall function, and then IERC20 is just going to help us do some token function calls. You can ignore this interface for now. This is just used for the scripts that we will go through later on. The main contract here, or the only contract here, is the source greeter. And you can see that in the constructor, we're going to pass in the address of the Connext contract on the origin domain. And we're also going to pass in the address of the token that we're working with on this domain. In this case, it's going to be a test token because we're on testnet, and the Connext address. All of these addresses for the tokens and for Connext addresses can be found in the docs as well under resources. So for this workshop, we're working with testnet contracts, and you'll find the core contracts, the assets, and all their addresses in all these available chains. So back to the source greeter here. In the constructor, we've passed in those values. The main function that we're working with right here is xupdate greeting, which is the function that's going to be called by a user to trigger this cross-chain update. So you'll see here that it's going to pass in a target address, which is the address of the destination greeter contract that we're going to deploy after this. It's going to pass in the destination domain, which is the specific domain of the chain. So actually every bridge basically has its own mapping of domain IDs. So for Connext, we have ours listed here. The first thing that's happening in this function is there's a require statement, because the user is going to be sending funds to the source greeter contract, and then the source greeter contract is going to be sending those funds into Connext. That first leg of the transfer is going to require that the user does a token allowance approval. So this is just checking that that allowance has been done. And then the user is going to have those tokens transferred into this contract. This contract is going to do a similar approval to Connext, and we're going to have call data encoded, which is going to be the call data sent into the xcall. So to understand like what you need to pass in here, we need to take a look at what the destination greeter function requires. So what we're going to be calling is ultimately this update greeting function. And you'll see that it takes a string memory new greeting. So any string that you want passed in is going to be used as the new updated greeting. So for the call data that you need to pass into xcall is going to be an encoded string. And you can see that that's also passed in as a parameter to this call, so the user can specify whatever string they want. The other parameters here are an amount. So the amount of tokens that you want to send in with this. And one thing that I forgot to mention at the beginning here for the context of this example is that this greeter contract is actually going to require that some payment is made to update the greeting. So just to create a use case for why we're sending tokens into the call as well. Basically that update greeting function is going to be okay as long as you send any amount of test tokens greater than 0. So that's basically what the user will be sending in here for amount. Anything greater than 0 will work. Slippage is the other parameter that needs a little bit more sort of context, but for now, we are just hard coding that to 10,000, and this is denominated in basis points. So 10,000 is equivalent to 100% slippage, and we'll talk about like what the slippage actually means in a moment here. The last parameter that we're going to feed in is the relay fee. So you'll notice that it's passed in as the value to this xcall. So what you're doing is you're actually passing in the native asset as the relay fee. And the relay fee is this fee that's paid to off-chain agents to actually execute your call on the destination chain. So if you recall up here, once you do the xcall and the off-chain relayers do their thing to route this message across the chains, somebody has to kind of trigger the call on destination, like somebody with gas. And in most cases, you don't want that to be the user, because some users might not have gas on the destination chain, and they will basically be constructing a meta transaction for relayers to submit on their behalf. So in order to incentivize those relayers to trigger that transaction on the destination chain, you have to offer them some kind of incentive. And that incentive is this relay fee that we're passing into the xcall. Now, what you actually use as the relay fee is something that you have to estimate. And we have an SDK that you can use. So back to the docs here, under the SDK, you'll find that the base class has an estimate relay fee function. And you can basically construct this in any kind of like node environment or front end, pull in the Connext SDK, and then call this estimate relay fee using the origin and destination domain parameters to determine how much this relay fee needs to be to incentivize relayers to actually to move the transaction along on the destination side. We will eventually have off-chain methods or on-chain methods to do this, but for now, this is a fully off-chain calculation. And for the purposes of this example, we are actually just going to hard code the relay fee as well. to some value that is a conservative estimate that should go through. All right, so okay, let's look at the destination greeter now. So for the destination greeter, you will also have to import a couple of interfaces. The main one being this IX receiver. This IX receiver says that any target contract that's going to be called by Connext has to implement an xreceive function with exactly these parameters passed in. We're not using a couple of these in the function, that's why it's highlighted here, but you can kind of just ignore that for now. But basically, if you are going to capture any xcall on the destination side via a contract, that contract has to implement this function. And you'll see that in the constructor for this destination greeter, we're also taking in the address of a token, and this is going to be the test token on the destination side. So in the xreceive function, we first check that the asset coming in from the xcall is the right asset that we've instantiated this contract to take in. And it also is enforcing that cost that I mentioned earlier. So anything greater than 0 will be okay for this contract to update the greeting. And then what we're doing is unpacking the call data that came in with the xcall. So this encoded call data is being unpacked on the destination side. So new greeting is decoded, and we're calling update greeting with that decoded new greeting string. And that's really it. That's the source and the destination. And in the README of the Zap Starter Kit, if you scroll down a little bit, there will be a deployment section where we already have built out a bunch of different Forge scripts that can do the contract deployments, and it can do the function calls without you having to, muck with MetaMask and go to Etherscan and interact that way. So there's a very simple make command that you just run to deploy the source greeter and the destination greeter. And you'll see that in the .env example here, there are a bunch of different variables that you need to fill out. So your private key, Etherscan API key for verifying the contracts, and anything that's between these like brackets are variables that you need to fill out eventually. We do have some filled out already, and this is assuming that you're sending from Goerli to Optimism Goerli. It already has the origin destination connect contracts, the domains, and the tokens filled out. The default is to send one test token, to use 100 as the slippage, and I believe this is 0.03 ETH as the relayer fee. So when you look at this and you deploy your contracts, it's going to show you the address of where that contract was deployed to. So for the greeter example, you'll want to fill out the address of that greeter and the address of the destination greeter, and then you'll also want to update like what the new greeting you want will be. Because the next step after deployment is to actually test it. So we also have Forge scripts that call the xUpdate greeting function here already. And you can find all these scripts under script. So script greeter, destination greeter.s.sol, and source greeter.s.sol are the deployment scripts. And then update greeting is going to be the script that actually calls xUpdate greeting. So what it's doing here is it is minting you some test tokens. So if you forgot or didn't actually mint yourself some tokens earlier, this script will actually do it for you automatically, because the test token on testnet is freely mintable. And then it will approve the token allowance from your wallet to the source greeter contract. And then it's going to just call xUpdate greeting with all of those parameters filled out, most of those coming from the .env. So once you run, Once you run the make update greeting command, which is going to run this Forge script, you'll see a transaction hash that pops out, and you'll be able to actually track the status of that transaction hash. So in the interest of time, I'm not going to go through and actually deploy these contracts. I'm just going to use 2 pre-deployed ones. So the source greeter on Goerli and a destination greeter on Optimism Goerli. And we'll just take these addresses and we'll fill out our .env here. So down to the greeter, yeah, I already have these filled out, but the source greeter address from Goerli, and then the destination greeter address from Optimism Goerli, and then some new greeting that I want. And then I will just run the update greeting command, which is make update greeting. This will start the forge script. It will go through all those steps that we just looked at, which is to mint and approve and call update greeting. Forge is relatively fast, so we should see our transaction pop up here. All right, there it is. There's the hash on Goerli. If we look this up, we can see that it is still pending. But now the next step is to kind of determine at what state your transaction is in. So you want to track, like, I sent the xcall. What's its current status? And so in our docs here, we do have a section to show you how to track these xcalls. One method is to query the subgraphs directly. So you can navigate to the reference, go to subgraphs, look at resources, and then all of our deployed subgraphs are going to be here. So you can do something like open the Goerli subgraph, paste in the sample query to find all of the details of the xcall. Alternatively, you can just look at our Explorer UI, which is, sorry, it's in this page, which is going to be here. It's at testnet.connectscan.io. And you can just input any transaction hash. So the one that we just sent, we'll look that up in the Explorer here. And you can see that there's already a registration here. So we're already tracking this xcall. It has been sent on the destination, on the source, and we're just waiting to have that be received. Awesome, there it is. So after about a minute, this was received, and we can look at the transaction hash if we want to, just to see the assets actually being delivered. So the test token was delivered. And there will be another part of this that gets filled out called reconcile, and that's a different state. That's basically when the routers that are in our system providing fast liquidity get reimbursed. But from an end user perspective, the receive is all they really care about, because that's when their assets get delivered. So not only do the assets get delivered at this point in time, but the destination contract also gets called. So what's happening is that Connext, let me get back to the right page here. On the receive, Connext is going to call xreceive on the target contract. So if we look at our destination contract again, which is here, and you can see that we had this xreceive. This xreceive was called, and the greeting was actually updated to what we specified earlier. So this is an example of an unauthenticated call with asset transfers. And this was pretty simple. The transaction went through pretty quickly, and that's because we didn't actually have to wait for any kind of validation by the bridge, because the function on the destination side was open and callable by anybody. In contrast, if there are a lot of use cases that require this sort of authenticated call, and what we mean by the authenticated call is the destination contract, so that xreceive actually requires some kind of permissioning. So there's access control that's implemented in that function call. So something like an only owner modifier, where it checks like who's calling this function and do they have permission to call this function. That's what makes something authenticated. Now, with an authenticated call, we actually can't fully short circuit this this bridge validation, and we actually have to wait out the full fraud-proof window. So that's kind of the drawback for authenticated calls. You are able to check who the original sender is and make sure that there are these access controls in place, but you will have to wait out a much longer latency period for that call to go through. So just to show you what this like authenticated call looks like, we'll look at the greeter authenticated contracts. So destination greeter authenticated and source greeter authenticated are the authenticated versions of those greeter contracts. Looking at the source here, it is basically doing the same things. I should mention that for this authenticated contract, just to make it, or example, just to make it slightly simpler, we did not include an asset transfer as well. So this one's not sending any tokens, it's just doing a call data call, but that function call on destination is going to be permissioned. So for the source here, actually everything is basically the same, except for there's no token, so no approval dance, none of that. We pass in 0 as the amount, 0 as the slippage. We use address 0 for the token, but we are still encoding the call data for this greeting. So everything else is the same for the source. For destination, however, we're still importing IX receiver. It still needs to have the xreceive function, but here we implement this only source modifier. And what it's doing is ensuring that only the source contract is allowed to call the xreceive on this destination. So in xreceive, we do get the origin sender, so the address of the contract that actually called xcall originally, and we also get the origin domain. So what we're doing here is we're passing in those values to the only source modifier, and this modifier is checking that the origin domain and the sender address are from who we expect. And who we expect is, when we initialize this contract, when we deploy it, we actually specify the origin domain and the contract. So this source parameter, for example, would be the address of the source greeter authenticated contract that you deploy on Goerli. And it also takes in the address of Connext on this domain. So the Optimism Goerli Connext contract would be specified here. And then the origin domain would be Goerli's domain. So this modifier is expecting the original caller to be that source contract and for that calling domain to be the domain that you specified in the deployment here. And it's also checking that the caller of this contract is the Connext bridge. So all three of these requirements make it so that nobody else can call this function except for the source contract itself. So under receive, we apply that modifier to the xreceive, and we just do the same thing. We just decode the greeter variable, we send it into the update greeting function, and it updates the greeting. That's really the only difference in terms of implementation, but it does have a lot of caveats in terms of like the timing for an xcall to finally go through. In most cases, this is going to look somewhere between an hour to 3 hours, depending on the source and the destination chains, and their canonical bridge latency windows. But the sort of benefit that you get from this is that you can now create cross-chain protocols, cross-chain calls that actually do require some kind of permissioning. So this would be useful for DAO governance, for example, or anything where you don't want like public ability to call those functions. And similarly to how we used Forge to deploy the greeter unauthenticated examples, the Zap Starter Kit also has the same kind of commands to deploy those for the authenticated examples. So these make commands will basically look at your .env file, and it will take all the parameters here. You will also want to fill out these addresses as soon as you're deploying them. as soon as you've finished deploying them, update the new greeting, and then you can run the X update greeting, but for the authenticated version, which is right here. So make update greeting auth will call a different set of forged scripts for the authenticated example. So earlier we were looking at these, but the authenticated examples will be using these forged scripts instead. And these are actually simpler because there's no, like I said, there's no token dance happening with the authenticated example. It's just a super simplified example to show you how authentication will work. And the main meat of that is going to be on the destination side, where there's some kind of modifier or within the function that you're calling, there's going to be a check for the origin domain, the origin sender, and making sure that the caller of X receive is Connext. All right, so that's basically it. There is a slightly more complicated example that you can go through if you want to mess with multiple hops with xcalls, and that's going to be this ping pong example. So it's what we call nested xcalls, where you can send an xcall within an xcall. We have two contracts here, ping and pong. Ping will call xcall. It will deliver some encoded data to pong, which will also use that encoded data to call an xcall back to ping. So in this case, ping and pong both implement IX receiver. So they both have this xreceive function, and they will both use xcall. So this is an example of how you can kind of chain xcalls together. And they don't always have to go back to the same chains. So you can do things like xcall from chain A to chain B, and then xcall from chain B to chain C. Or you can go from chain A to chain B and then back to chain A, and kind of use this pattern as a sort of callback mechanism. All right, so that is pretty much it in terms of looking at the examples, but I did want to also run through some important considerations, which you will definitely run into when you're building these kinds of cross-chain applications. The first topic is, we already touched on this a little bit, but it's how do you estimate those relayer fees? There are actually two kinds of fees in the Connext ecosystem. One is the relayer fee, which is the kind of like a service cost for relaying meta transactions on the destination. And then another fee is a router fee. So this is a hard-coded 0.05% fee of the asset that you're bridging, which is going to be taken by routers for providing you the service of that sort of fast path execution. Normally, all xcalls have to go through, well, actually, all xcalls do, in fact, go through this sort of like slow path where it has to wait out the full window of the bridge's validation window. But if you're sending assets that our decentralized network of routers are providing liquidity for, those routers can actually front the funds for the user on the destination chain, and basically provide them those funds ahead of time. So the user gets their assets immediately on destination, and the router takes up that lockup window for an hour to 3 hours, and then they finally get reimbursed the funds. So for their troubles of the lockup and fronting the costs, the user pays 0.05% fee to the router for that. Now, for the relayer fee, because we mentioned that there is this off-chain method to calculate the relayer fees, and this really depends on like gas prices and the current state of gas on the origin and the destination chain. Sometimes the estimate will be under what is actually necessary for the relayers. Like maybe there's a gas war and causes a gas spike, and the relayer fee you sent in is not enough for relayers. If that's the case, the user has to bump the relayer fee. So there is a way to actually do this directly through the contracts. So you can call this bump transfer method on the Connext contract. on the origin domain. Or if you go into the UI for the Connext scan, some transfers you'll see here, like this one, for example, has a low relayer fee. And the user will be able to see like, okay, I sent the xcall with 0.01 ETH. That wasn't enough. I actually needed to send this much more. So this scanner site actually lets the user bump their relayer fee themselves and be able to see like what the issue was with the xcall if it didn't go through. The other caveat that I wanted to talk about is it's not the relayer fees, but it is the slippage. So if you recall, we were passing in a hard-coded slippage value for the greeter example, the unauthenticated example. So source greeter, we were passing in slippage as 10,000. So this means that for this example, we're just willing to take 100% slippage on the transfer. And that's fine for this kind of like play example, but on mainnet, on a real protocol, slippage is something that your users will probably care about a lot, and you should be allowing them the option to set the slippage as they want. But similar to the relayer fees, if the slippage is too low, then the xcall will not go through fully. And similarly, you'll be able to see the status of that. And let's see if we can actually find one here. So a low slippage error is going to look like this. And for this, you're going to, the user is going to be able to bump that slippage percentage. And this is going to be done on the destination side. So there's actually a little bit more complexity to this slippage component. And we'll take a moment here to actually just like dive into that. So what exactly is the slippage? Why is there slippage when you're sending assets? Yeah, let's talk about that. So the reason there is slippage is because when we send, let's look at the assets actually. When we send an asset from chain to chain, the asset that we're sending and receiving may not be the assets that we actually want to use on those chains. So every asset has a canonical domain, meaning this is the domain where the asset was originally deployed to. And then when those assets are bridged to other chains, they are delivered as representations of the canonical asset. So let's take a look at the testnet ones, for example. We have two assets on testnet, test and Weath. They are both canonical on Goerli. So this specific asset is the one that was originally deployed on Goerli, and it's also the one that's used by everybody else. So all the DEXs, all the other protocols, they're all using these assets on Goerli. So when I bridge a test token from Goerli to Optimism Goerli, this canonical token is actually locked on the Connext contract on Goerli, and then Connext mints a representation token of this test token on Optimism Goerli. So when test is then bridged the other direction, this test token is burned on Optimism Goerli, and then the canonical locked token on Goerli will be unlocked. The big distinction that you need to make here is that sometimes the representation token that's delivered on destination is not actually the token that everybody else is using. So in this case, the test token, which Connext deployed, is the one that's being used on Optimism Goerli. But Weath, for example, actually has a sort of a market decided flavor of that token that's being used by other protocols on testnet. But the flavor of Weath that connects to actually mints on Optimism Goerli is a different token. So that's what we mean by a local token versus the adopted one. The adopted one is the version of the token that everybody else is using, and the local version of the token is the one that Connext actually mints. So because there's these two different flavors of WETH on Optimism Goerli, we want to give the users the one that they actually want, which is the adopted version. But Connext mints the next version of that token instead. So what happens under the hood during the xcall, on the origin and the destination side, there potentially may be a stable swap pool of the next asset and the adopted asset. And because they're always, because the next version of the asset is always redeemable 1-to-1 with the canonical, it has equal value. And so we spin up these stable swap pools, which you can see on our actual, like this is mainnet, and these are the stable swap pools for USDC and WETH on these different chains. So liquidity providers are going to provide next asset and the asset into these pools, and then the xcall is going to swap in and out of these assets depending on whether there is an adopted or a difference between adopted and a local token on those chains. So potentially for every xcall, you can have up to 2 stable swap pools that you're swapping in and out of. And so the slippage parameter that we're sending in to the xcall is your user's acceptable slippage limit for both of those swaps. Every time you do a swap in a pool, you incur some kind of slippage. Sometimes it's positive, sometimes it's negative. But at a certain point, the user doesn't want to go below and swap like 1 ETH for 0.99, for example. And so their limit at that point would be 1%. And this slippage is the total slippage amount. So if I'm swapping a token from Goerli, sorry, let me get a good example of this. If I am swapping, here we go. If I am swapping a adopted token from a chain where it's not canonical, so USDC on Optimism is not canonical, and USDC on Polygon is also not canonical. If I happen to swap the adopted version, which is USDC, which is most of the time, Connext can only bridge the next flavor of that token. So when we're doing an xcall and sending USDC from Optimism to Polygon, it's first going to be swapped from USDC to next USDC, which incurs some kind of slippage. And then on the destination side, Connext is going to mint next USDC and then swap it into USDC to be delivered to the user at the final side. So in this case, there are actually 2 swaps that are happening. You are free to send the next version of these as well from chain to chain, or receive them if you want. And in those cases, you will not incur slippage. But for the majority of cases, and for most composability purposes with other protocols, you are going to be sending and receiving the adopted asset. And so this slippage parameter is actually very important. And sometimes you will have set the slippage too low. And in those cases, you'll have to go and actually bump that slippage. All right, so I know that was kind of a lot to digest. The Connext team is always available on our Discord server. So if you have questions about any of these examples, any part of the parameters, the slippage, the relay fees, how you build other kinds of contracts, we're always there and active to help out. So, don't be a stranger. Feel free to drop by, say hi, and ask us questions. Yeah, that's basically it. I know these were some very simple examples, but getting started here will kind of get you at a good state to start building your own protocols and exploring this like wonderful new world of cross-chain applications.